Hello, this is chapter 4, video number 6. This one's going to be a short one, but I have two words of caution with regression. You don't want to be on my list of bad stats or bad math. So these are two things that you would like to avoid. First off, avoid extrapolation, meaning if you have data around a certain domain from some score to another score, don't use it too much to predict the future. So here is my example. Let's go back to the interpreting lines of best fit. And most students in this class scored somewhere between studied somewhere between 2 and 8 hours. Well, let's say somebody sees this equation and says, aha, I have the fix. I myself am going to study for 20 hours. Ha ha ha. All right, so that'll be sure to beat it. So if I were to use this equation to predict the score of somebody that studied for 20 hours, all right, so well, let's take a look at what I would end up with. When I type that in, I end up with a test score of 156.91%. Ha, that'll show them. No, this equation was used on the domain from 2 to 8 hours, typical hour studying from 2 to 8. Um, so that really should only be the values that we use to make predictions for. For students who scored between 2 and 8 hours, here's what we've got. Not 20 hours, that's ridiculous. And the same can be said for some COVID data. If you were to zoom in here, this was the number of cases outside of China in days. So after 36 days, there were 3,323 cases outside of China. On day 37, 4,288, so on and so forth. And this looks like a nice linear regression. If we only use that data, we'd say, look at how beautifully linear that is. But if you've been paying attention to the news, this is not linear. So even though if you zoom in close enough, it does look like a straight line, it could only be used for those values. Overall, it does not look like a straight line. All right, so that is your first warning. First warning is avoid extrapolation. Only look on reasonable domains and reasonable values for inputs. And the last one is correlation does not equal causation. Just because you have a really strong, really strong R value does not necessarily mean that one caused the other. So I want to go ahead and show you guys some weird correlations here. All right, this website shows some weird things that are correlated, but definitely do not cause each other. So this one, divorce rate in Maine and per capita consumption of margarine. This has an R value of 0.992558. That's super strong. And looking at these, wow, it really seems like margarine and divorce rate are one causes the other. I don't know whether divorces cause more margarine consumption or what, but just because two things are correlated does not mean that one of these cause the others. Same thing here. Number of people who drowned by falling into a pool, and Nicolas Cage appeared in that year. So taking a look at it, seems like when there's a peak of Nicolas Cage movies, there's also a peak of drownings. However, one does not cause the other. The only way to determine causation is a good experiment where you're actually manipulating the data and then measuring. So just because two things look like they're associated. This one is per capita cheese consumption, a number of people who died by becoming tangled in their bed sheets. No, cheese consumption does not make you get tangled in your bed sheets. That's ridiculous. So those are my words of caution. Avoid extrapolation. And finally, just because two things are correlated does not necessarily mean that they are cause and effect.